Sorry class, I'm out again today. This would be the reason why. That's William. He has a fever again, although he's feeling a little bit better, so I also apologize if you hear him in the background. But it's getting to be a little bit crunch time, so let's talk about capacitors, specifically capacitors charging with a DC current. So a very popular kind of problem is where you have a capacitor, remember C equals Q over V, in series with a resistor. So we close this switch and it makes a series circuit. You have the battery, you have the resistor. Let's talk first about what happens initially. The charge, the current is very, very high. It's initially the same as if there was no capacitor at all. So it's going to be V or E battery over whatever resistance, and then eventually it drops. The reason it drops is on this capacitor, initially there's no potential difference, but as you keep piling more and more and more charges on there, it does have a voltage. So this voltage of the capacitor is going to be Q at whatever time that is, divided by C. So let me first show you what that looks like, the results we get, and then we'll go through the derivation of why you get what you get. So I made a little spreadsheet like I do for everything. Now, the amount of time it takes to charge up this capacitor depends on the capacitance, the resistance, and the size of the battery. We can change those things here. The way we describe the time is in something called tau, or the time constant, and that's R times C. You'll see why that is. So I've graphed this from 0 to 5 time constants. Now we can display it as raw values as the capacitor charges up, or you can display it as a fraction. The reason we can display it as a fraction is that the capacitor, the amount of charge it will ultimately end up with is the same as the charge it would have if you connected it directly to the battery and let it charge up. In fact, when you look at the graphs here, that charge is going to be equal to CE. The reason, again, C equals Q over V, so Q equals C times V, V being the voltage of the battery. It takes time. In the beginning, it's very easy to put charge on because there's no opposing voltage, but as you put more and more and more charges on there, they're going to oppose you trying to push more charges in. So it's going to get smaller, smaller, smaller as far as the amount of charge you can put on there. And you can see that when you look at the graph of the current. In the beginning, there's a high current as this thing's trying to charge up, but then you have more and more resistance because the capacitor has a voltage that is now opposing that, and the current drops off. The amount of current it has in the beginning, that I naught, is going to be the same as the battery voltage divided by the resistance. In the beginning, the capacitor doesn't make any difference because it doesn't have any charge, and it doesn't have any opposing voltage, but over time that builds up. And the voltage of the capacitor, as you can imagine, approaches the voltage of the battery, E, but initially there's no voltage. So let's talk about why that happens. So if this is your circuit, all we have to do is we have to apply Kirchhoff's loop rule. Basically, the energy as you go around the circuit has to add up to 0. So if we draw it as we did there, when we close the switch, we want to put this on the right. I'm sorry. And the battery voltage, as you go around, you go through the capacitor, and going through the capacitor is kind of like we talked about going through a battery backwards, going from the positive terminal, from the positive terminal and negative terminal. So that's the voltage of the capacitor minus the current times that resistor, and that has to add up to 0. Now, to make life a little bit easier, I'm going to multiply everything by C. So that's CE minus, now VC, if you recall, because it's a capacitor and V equals Q over C, that's like Q over C times C, that's just Q. Come on. Minus. Now, current is a rate of change, dq dt times r, and that has to equal 0. Then what I'm going to do is I'm going to actually move some things around. I'm going to leave this on the left side minus dq over dtr, and that's going to be equal to, now when I bring the other stuff over, that becomes positive q minus ce. Now what we're going to do is separation of variables. So we want to get the t stuff on one side and the q stuff on the other. So you wind up with minus, whoops, drop the c here. Forgot to put the c there. You wind up with minus 1 over rc dt equals, now I have to bring the q minus ce over to the dq side, which is going to give us 1 over q minus ce dq. We have to integrate both sides. Now, as far as what we're going to integrate from, let's just call this from time 0 to some time in the future. I'm going to call it capital T. And we're going to integrate from no charge on the capacitor to some final charge we'll call plus q. Now, on the left, that's easy. Integral of dt is t, so that's negative t over rc is going to equal. Now, you may or may not remember the integral of this. It's like taking the integral of 1 over x. Remember, is ln of x. So we're going to take the integral of that, and that is going to be the ln, natural log, of q minus ce. And the limits for that are going to be from 0 to q. Now, when we plug this in, that's like the ln of capital Q minus ce minus the ln of, well, you plug in 0, 0 minus ce. Log rules, that's the same as dividing. So ln Q minus ce over negative ce. I'm going to take the way you can undo natural log is to take base e and raise both sides to that power. So on the left here, we wind up with e to the negative t over rc equals q minus ce over minus ce. Or I'm going to rewrite that negative. That's like switching that. So ce minus q over ce. Which is going to be the same as 1 minus q over ce, e to the minus t over rc. Now I want to get q by itself, so that's going to be 1 minus e to the negative t over rc equals q over ce, or the charge on the capacitor at any time is some fraction of Ce. Now that makes sense. That's the amount of charge you have when the capacitor gets to the same voltage as the battery. But it's some fraction of that. So it's always that or less. So it's 1 minus e to the negative t over rc. Notice as t gets bigger, this is going to get bigger, which makes sense. So as t approaches infinity, q approaches ce. In the beginning, when t was 0, that's like 1 minus 1, q equals 0. That makes sense. I should probably make sure this is still recording. I am. The question is, are you still listening? So we have an expression for the charge at any time. Now we're also interested in the voltage and the current. Well, voltage is going to be the same as Q over C. So all we do is we take this and we divide it by C, because V equals Q over C, and that's going to give us that V is simply E times 1 minus e to the negative t over RC. And that makes sense. In the beginning, the capacitor has no potential difference, and as time goes on, it gets closer and closer and closer until at some time infinity, you actually reach the battery voltage. What about I? Well, what's the definition of current? The definition of current is dq dt. So I is going to be dq dt. Baby's still alive, that's good. And that is going to be taking the derivative of that. Now when you take the derivative of 1 minus e to the minus t over rc, well, CE, the derivative of 1 isn't anything. Now minus t over rc, so that's minus from the formula. And then when you take the derivative of e to the minus t over rc, you get the same thing, but don't forget to take the derivative of that, which is going to be negative 1 over rc, which is the same as positive. So the c's cancel, and what you wind up with is that the I, the current in the circuit at any time, equals E divided by R. That's interesting, the battery voltage divided by the resistance. This is also known as I naught times E to the minus T over RC. So you wind up with this thing that is an exponential decay. So here's the third equation that we need to know. So when we look at our graphs again, that's why we get the shape that we get. Now, the most important thing to understand in these as the capacitor is charging is that they are each approaching a limit. So the charge in the capacitor is approaching the limit CE. The voltage is just charge divided by C. So it looks the same, it's just the numbers are different. At least they would be if I show you the actual numbers and not just a fraction. And the current initially is very high. It's the same as if there was no resistor. It was the same as if there was no capacitor at all, and then it drops off to 0. It's an exponential decay. And that's what we get there. Now let's talk for a second about this tau. That's why I have this display as fraction button. So this time, our time constant tau for this particular resistor and capacitor is 22 seconds. So that means at 22 seconds, we've had 1 tau go by. At 44, we've had 2 taus. What does that even mean? Well, 1 tau is the same as 1 RC. So that's some fraction, because as you can see, the charge and the voltage are some fraction of the battery voltage and the CE. That fraction is 1 minus e to the minus t over rc, the time constant. So in the beginning, they're both 0, and then they increase rather rapidly in the beginning, and then less quickly, less quickly, less quickly. Well, if you look at the time, in terms of time constants here, if we go to 1 time constant, what that's telling us is that you have 36.7% or 63.2%, because it's that or 1 minus that. So at 1 time constant, what that means is that the voltage is that fraction of, the charge is that fraction of that. Hold on, let me pause this so I sound like I know what I'm talking about. Okay, it's a little easier to explain. I put it at exactly 1 time constant, which gives us the charge is 63.2%. Why 63.2%? Because that's 1 over e to the 1. If I go to 2 time constants, You wind up with 86.5. Why 86.5? That's 1 over e to the 2, etc., etc., etc. But the charge on the capacitor approaches CE. The current starts at V over R, meaning V of the battery, and drops off to 0. And the voltage across the capacitor looks exactly like the charge over the capacitor of the capacitor, just divided by C. So I'm going to give you guys a problem that you can work on with the capacitor charging, and tomorrow I will definitely be in class. My wife is on a plane. She says she's going to be here. So even if he's sick, should be there. But charging and discharging of capacitors are like one of the AP C exam's favorite things to do. So hopefully this is better than me not saying anything at all today. We'll find out.